All right, now that we have all the naming for our organic families out of the way, we're going to look at some of their properties. So for the most part, we're going to be looking at boiling points, their solubility, and we're also going to be looking at probably a few other things as well. So what we have right here is we know organic compounds are made of predominantly 3 different types of bonds, and then of course the polarity of these bonds determine the intermolecular forces. So this is going to call back to Chem 20, and we already looked at a little bit of this too when we did kind of our first little introduction to organic. So you have to remember that our carbon to hydrogen bonds are always going to be nonpolar. So if you have an alkane, alkene, alkyne, or even our aromatic, they only contain carbon and hydrogen bonds, so they're nonpolar. If we see our hydroxyl functional group showing up, so like in our carboxylic acids and our alcohols, of course this OH is going to be a very polar group, so we have our London dispersion, dipole-dipole, and hydrogen bonding. So these are the strongest intermolecular forces. And finally, the last one, if we see that C double bond O, or the carbonyl functional group, so these are just normal polar. So there is no hydrogen bonding, and of course if it's just polar, London dispersion, and dipole-dipole. So one thing you have to remember for, of course, solubility is that like dissolves like. So you can use this to help separate organic molecules from different reactions. And the first thing we're just going to look at is something called solvent extraction. So this is just a method used to separate compounds based on their relative solubilities in 2 different immiscible liquids, usually water and organic solvents. So organic solvents are generally nonpolar. So we use this whole idea of water, which is polar, and use an organic solvent, which is nonpolar. We can separate things. So for example, let's just say we have a mixture of this ester and this carboxylic acid. So where these two are generally liquids at room temperature, of course they're kind of interacting. There's no water present, so we just have this mixture of both organic stuff, and these are both kind of polar as well. So if we toss in some sodium hydrogen carbonate, which is a base, and of course it is aqueous, so that means we have water in this base. So you'll notice that we have a carboxylic acid, so we end up getting an acid-base reaction. And we're going to remove this hydrogen and create the ion, which we can see right here. Now, after we mix 2 of these here, we'll notice our organic layer is up at the top right here. And this is our aqueous layer right here. So our aqueous layer, obviously aqueous water being extremely polar, so it's going to dissolve all the polar things. In this case right here we have our ion, so sodium ion, and we have this right here because it's negatively charged, so all of our polar stuff is going to get drawn into this aqueous layer. And then our non-polar, so like even though this is slightly polar here, it's going to be more kind of non-polar-ish compared to the water. So we have our organic layer still kind of goes at the top there. So that's just a little bit on solubilities. Now, boiling points, if you remember, we can use these, and it's based on compounds' polarity as well. So if you remember, more higher or more intermolecular forces equals a higher boiling point, and so on and so forth. So we have a little chart here that kind of has the organic family, the intermolecular forces, and of course their boiling point. So it's carboxylic acids because it has the carbonyl functional group and the hydroxyl. There's 2 functional groups here. It has London dispersion, dipole-dipole, and hydrogen bonding, so it is always going to have the highest boiling point. Now if we notice when we go down, our next one is alcohols. So it has same thing, it has a hydroxyl functional group, so it has a hydrogen bonding. But where it's only the 1 functional group, that's why it's a little lower in carboxylic acids. Then our next in line, we have esters and organic halides because these are going to be polar. Esters because of the ester functional group, organic halides because of the halogens. And the ester functional group is a little more polar than the halogens, so that's why esters are going to be up top here. And then of course we have our aromatics, alkynes, alkanes, and alkenes. So you do have to memorize the order that these occur in. And this is the order from highest to lowest right here. Alkenes having the lowest boiling point out of any single organic molecule that's there. So big thing is just kind of using this chart, and we have stuff right here. So example 1, put the following organic compounds in order from highest boiling point to lowest, right? So we're just kind of looking at the chart, and these here are just kind of chunked out a little bit. So we have our carboxylic acids, that's going to have the highest. Next our alcohols, then our aromatics, then our alkanes, then our alkenes, right? Remember, alkene is always the lowest. Now, this is more of a typical example right here. Instead of just looking at the families, we have just organic molecules as they appear. So, of course, when you're looking at this as general formulas, it's handy to know what family they belong into so we can start putting them into their groups. So for this one here, we got C2H6. This is in the formula of CnH2n plus 2, which is an alkane. We can see the OH, alcohol. We can see COOH for this one right here, so this is a carboxylic acid. And finally this last one right here is in the form of CnH2n, or an alkene. Alright? So just like before, if we want to place them in order of highest boiling point to lowest, the highest one is always going to be the carboxylic acid. So of course, if we wanted to draw that one out, we can, or we can just write the formula. So CH3COOH is the highest. Next, we're going to have our alcohol, so C2H5OH. Next, our alkane, so C2H6. And then finally, our lowest is our alkene, C2H4. And that's just kind of predicting which one is going to be the highest or the lowest. Now, for example 3, we're drawing 3 isomers of pentane and arranging them from highest boiling point to lowest boiling point. So before we actually get into that, I want to bring up this little sentence right here. So if you read it earlier, that's awesome. If not, it'll kind of make sense as we go into 3. So what we have here, the boiling points of various organic molecules can be determined by how many branches the compound has compared to the straight chained isomer. So one thing you have to remember, more branching equals lower boiling point. So going down to this one right here, example 3, now our 3 isomers of pentane, we have our straight chained, which is just 5 carbons, 1, 2, 3, 4, 5. Now in order to get that, remember, in order to draw an isomer, we are going to have to remove an N carbon and then put it somewhere in the middle. So that means we're going to have a butane, looks like this, and of course our last isomer is going to look like this. Right, so we got pentane, we have methyl, butane, and dimethyl propane. So these are the only isomers that we have for our pentane. Now, just from up above where it said that the more branches we have, the lower the boiling point. So in our straight chained alkane right here at pentane, we have 0 branches. So it should have the highest boiling point. Our methyl butane has 1 branch. And our dimethyl propane has 2 branches. So this one should have the lowest boiling point based on the rules above. So that's where we have our little, you have to remember the families and the order, and then of course the whole branching thing as well. Now, this is something else you will kind of have to have memorized. I know, sorry for all the memorization, but it's just kind of how we have to go about it. And that is kind of when we get organic molecules that are big enough, because we are increasing the carbon to hydrogen bonding, which are nonpolar. If the molecule gets big enough, it is going to turn nonpolar. So insoluble organic compounds, this is in water, of course. So all aliphatics, no matter what, they're nonpolar, and aromatics. Now, just pay attention to the alcohols, esters, and organic halides right here. We have alcohols, so large molecules. So the general rule is above 7 carbons. So if you get like octanol, nonanol, and decanol, it doesn't really matter if it's decan 1-ol, 2-ol, 3-ol, or 4-ol. It's going to be nonpolar because it's just so large. Same thing with the esters, so more than 5 carbons in total. In organic halides, you can even use kind of the same rules as well as the esters. We'll go 5 plus carbons. I know this depends on the shape and size, but we'll just kind of worry about the size. The shape is more of a university type organic chemistry when you get into that, specifically with organic halides and the alkene molecules and everything. Now, our polar ones, carboxylic acids, for right now, we're going to have, no matter what, you have a carboxylic acid going to be polar. And alcohols, so small ones, less than 7 carbons. Esters, less than 5 carbons in total. And organic halides, same thing, less than 5 carbons. And that's just something to kind of keep in mind as well. And like for the most part with a lot of the examples, you know, and not going to ask you, will heptanol dissolve in water where it's right at 7? Not going to get into that. It will be quite obvious if we're talking about large alcohols, so you're going to see like 10, 12, 13 carbons with a hydroxyl functional group. You know, it's going to be ridiculously large, or it's going to be small like methanol, ethanol, propanol, butanol, just those right there. Now finally, one of the last things before we get into petroleum refining and looking at more of how we refine stuff based on their physical properties is just another definition, and this is called the homologous series. So what this refers to is a sequence of molecules with the same family but differing only in the repeating units, or the number of carbons. So for example, we have the alcohol family right here, so methanol, ethanol, propanol, butanol, pentanol, and so on. So you can tell that these are differing in only 1 carbon. Now another one you can have is something like methane. And then jump right up, so skip ethane, go to propane. And then skip, go out to, what's next, pentane. And so on. So this is still considered a homologous series because we're keeping the same family. In this case right here, it is the alkane family, but we are just differing the number of repeating units. In this case, 1 carbon, 3 carbons to 5 carbons, right? But you can kind of see that we're just differing the number of carbons that are there. Now, as for this one right here, explain the predicted trends and boiling points in a homologous series. So, of course, this homologous series are we're increasing number of carbons. So as we increase the number of carbons, the boiling point will increase because of stronger London dispersion forces. Alright, so that's how you can predict as you go up a homologous series. We should see an increase in boiling point because we're increasing number of carbons and hydrogens, and of course that is creating a much stronger London dispersion force. Alright, now last little topic when we talk about all of these boiling points, stuff like this, is practical uses for it. So separating stuff after reactions is very useful, but one of the main ones we're just going to focus on right here is petroleum refining. Because when you look at petroleum, it's a mixture of hydrocarbons when we look down in the definitions, found in natural gas, crude oil, and bitumen. So of course separating these here is what we need because different hydrocarbons are going to be responsible for different things. So just some of the definitions right here. Hydrocarbon, we touch petroleum. It just mentions a mixture of hydrocarbons. We have petrochemicals. So this is hydrocarbon material from petroleum used to produce plastic and other synthetic things. Refining is just technology includes physical and chemical processes of separating complex mixtures. And one of the ones we're going to be looking at, distillation. So distillation uses boiling points to separate compounds. So, what does distillation look like? Well, it looks like this diagram right here, where we actually have a liquid mixture, where we heat it up. It's going to boil, so it's going to turn into vapor, and then eventually we want the vapor to then condense. So we use a little cooling thing right here, so it cools, condenses into liquid, and then finally we get something called the distillate or the liquid going out there. So of course this is distillation just really at its most basic level, where we separate things based on their boiling points, because if you have two things with different boiling points, one's going to boil before the other one. So once you boil it off, you cool it, condense it, and then you can get the liquid. Now, what they use to do this with hydrocarbons is something called fractional distillation. Because when we look at petroleum, there are so many different hydrocarbon chains there. We're just not going to like boil one thing and then crank up the temperature, boil out another one. Basically, we just kind of put everything down in the pot right here. And as we move up this column right here, it's really hot at the bottom because this is fire right here, right? And it gets cooler as we move up this column. So of course, as different things with different boiling points move up our main column right here, they're able to collect these, what we call fractions, at different temperatures. So for example, if you look at the big carbons down at the bottom have the highest boiling point, and as we start going up with different types of fractions here, right, so C17, and notice how the boiling points all go down, and of course the hydrocarbon chain also decreases as we go up. So this is fractional distillation because these things right here, these are called different fractions. So it just uses boiling points of compounds to separate the components of petroleum. Now it's just a little thing here for you guys to kind of read, and same thing, just kind of a big visual on the different boiling points and what some of the fuels are used for. Right, so like diesel and fuel oil and bitumen and lubricating oils and gasoline and stuff like that. Right, so this is kind of handy for you to look at and see what some of these petrochemicals are. Now, there are two reactions that you will need to know for petroleum refining as well. And that is, once, like, let's just say you have big hydrocarbon chains and you want to make them smaller. Well, one of the things that we can do is something called cracking, or thermocatalytic cracking. So this breaks longer hydrocarbon chains into smaller fragments. So it requires heat, pressure, and hydrogen. So you're going to notice you have a cracking reaction if you see a very large hydrocarbon chain like C17H36, right? So you can tell this one's very large. So if you add heat, pressure, and hydrogen gas, we're going to split it. So of course this one splits into C9H20 in this unknown product right here. Well, all you need to do is just kind of make sure the math equals out, right? So if we know one hydrocarbon chain is C9, or 9 carbons, the last one should be 8 carbons long, right? Because 9 plus 8 should equal 17. Now, as for how many hydrogens, remember, these are going to be alkanes. So you got CnH2n plus 2. So that should give us 8 times 2 is 16, plus 2 is 18. And of course, we can even look at the reverse. So if we know the two products, so C4 and C3, so two of those together is C7H. And of course, we do our math of CnH2n plus 2, so we get C7H16. So that is our cracking. Now, the reverse of this is called reforming. So it is the opposite of cracking. It requires heat and pressure again, and it produces hydrogen molecules. So of course, for reforming, so you just got to make sure that your math adds up. So if we got C7 here, H16 plus C12, H26, if we get 7 and 12 coming together, our new molecule is going to be C19, right? And of course, our chemical formula, CnH2n plus 2. So if you know 19 times 2 is, hopefully our math is right on this one, is going to be 38, and then plus 2, we get H40. And of course, we produce hydrogen. Same thing, ethane plus octane. Ethane is C2, H6, octane is C8, 18. So when we put these together, we add our carbons together because we're reforming, making this longer chain. So you got C10, H22, and finally our other product is H2. Now, I'd like for you to just kind of read this down below. It just talks about how fuels kind of get what is called an octane rating. So next time you're gassing up your vehicles, just look at the difference between your premium and everything like that. You'll notice they have different numbers, like 89, 91, and 92, I think are the ones that's there, or 94. Can't remember. But those are called the octane rating, and this just kind of explains on how they get that. Now, last little section is we have a bunch of different diploma examples using this here. Now, I would like for you to pause this video and go through, try to answer as much as possible, and I'm just going to basically fill it in as we go down through, fill it in and give a little brief explanation. But if you're not sure on any of those, just email me, or you can bring that out when we have our Google Meet sometime this week. All right, so pause this right now, try all the ones there, see what you get, and I'm just going to start going through all the answers here now in 2 seconds. All right, so for the first one, the answers you should get is 2, 3, 5, and 6. So of course with that, you're kind of just looking at this right here. You can tell that triple bonds increase boiling point because we're starting with our normal one right here. So it's negative 88.6 and it jumps up to negative 84.7. Same thing with our propane and propyne one. And we can tell the same thing with 3 double bonds decrease the boiling point. We have the hydroxyl functional group increase the boiling point, and chloro functional group increases the boiling point as well. The next one, we have fractional distillation tower. Hydrocarbons are separated based on physical properties, so of boiling point, compared to the number of carbon atoms in a molecule collected at the bottom of the tower. The number of carbon atoms in the molecules collected at the top of the tower is less. They're at the bottom, bigger, more intermolecular forces, higher boiling points. Up at the top, fewer intermolecular forces, so less. Our next one, your answer should be 2, 3, 6, and 8. So properties above of butane, so it's just straight chained, and of course it is nonpolar, it's straight chained. It's going to have a higher boiling point than propane because propane is only 3 carbons. And for this one right here, I know we haven't really looked at all the reactions yet, but right away undergoes combustion reaction. It's a hydrocarbon, you know it burns, so that's why you can choose 8. Now our next one right here, we have different compounds. So you're looking at trends going on here between the position of the bromine and boiling point and solubility. All right. So one of that we can conclude from this is that boiling point decreases as branching increases. So we can see that if we're looking at difference between this one, and this one. And next one right here. So it's not the same as the other ones. Like we have increased number of carbons, but we're going to take away the exact same idea. So using the solubility data in the table on the previous page, arrange the organic molecules number of decreasing solubility in water. So most soluble is going to be 3. And the reason for that, we know if we go back, we have this one right here, right, that had 2 branches on the same carbon, was the most soluble. All right. And then of course next we're going to have our branched, then this one right here. So we do get all of our hydroxyl groups out of the way first because they are going to be more polar and they have hydrogen bonding, so more intermolecular forces. And our last one is this bromine one here. Now for that last one, sorry if you tried this one and couldn't get it. Please omit this one. When I put this question in, I forgot about the types of reactions, and we're going to look at that next week. So after next week, we can go back and then fill this in. But if you manage to get this far, so propane can be removed for organic material known as crude oil, and the process is labeled fractional distillation. Now, last but not least, before we get into organic reactions, please have a look at this right here. It's just common organic families, their properties, and their uses. For the most part here, just look at the uses. You'll notice that all different organic molecules do have very common uses. All right, and you will need to be familiar with the general examples right here. So there's not a lot: methane, ethane, propane, octane, ethene, ethine, benzene, our chlorofluorohydrocarbons, a few alcohols, and one and ethanoic acid. So these here are just kind of general properties, but please have a look through and just make sure you are very comfortable with looking at a particular organic family and of course some of the general uses that they can have. All right. So next week we're going to be looking at organic reactions, and then that will be it for, I believe, the organic unit. All right. See you guys later.